Simon Albrecht with us at the IAC, and it's a pleasure to introduce him to you. Simon did his undergrad studies in physics in Hamburg. Then he moved to Leiden, to the Netherlands, where in 2008 he got his PhD thesis in astronomy. He finished his PhD at the Leiden Observatory. Then after that, in 2009, he got a Rubicon postdoctoral fellowship, and he moved to Cambridge, Massachusetts, to work at the MIT Kavli Institute for Astrophysics and Space Research. That's where I met him, and that's where he's still working today. And very recently, he has been offered, I learned last week, a junior faculty position at the University of Aarhus in Denmark. So today he will amuse us, and he will tell us all about spectroscopic studies of transiting exoplanets.
Okay, thanks, Manu. Yeah, thanks for the invitation. I would like to talk today about extrasolar planets, or exoplanets for short. In particular, I would like to address two subjects which I think are important. The first is formation, or in particular, the migration of gas giants. How do they move inward, close to their star, where we find them? And the second one is, how do we detect smaller, more terrestrial-like planets with radial velocity? Okay, so maybe to start our journey, a good place to start is our own solar system. In our own solar system, we have the 4 rocky planets on the inside and gas giants further out. And our system is very neatly arranged. When we look up at the sky, we see all the planets moving through the zodiac. All planets move in one plane. And they rotate around the sun also in the same sense, and that is the same sense as the sun rotates itself. So these observations and some other observations led to the idea about how solar systems, or in particular our own solar system, have formed. We have a young star in the middle, surrounded by a gas disk with about 1% of dust. And this dust can stick together, forming rocks and boulders, and eventually these rocky planets, which we see in our own solar system. If these planets get large enough, about 10 times the mass of our own Earth, then they get so heavy that they can accrete gas out of the surrounding, and you can form a gas giant, just like Jupiter, Saturn. We think that this formation of gas giants can only happen far out in the system, where it's cool enough that material can condense out, and these cores can form relatively fast while you still have a disk around. So having this picture, our one observation of our own solar system, we of course want to know, does it also apply to these other stars? How do these systems look like? And since about 17 years or so, we can find extrasolar planets, and we have been in for some surprises. I show 2 of these surprises here. On the y-axis, I show the eccentricity of these planets, which have been found mainly with radial velocity technique. And on the x-axis, I show the orbital period, which is a proxy for the distance between the star and the planet. And down in the right corner, we see our own Jupiter. And what's surprising about this plot is some of these planets have very high eccentricities, which we don't see in our solar system. And these are also all gas giant, or at least Neptune-sized planets. And some of these gas giants have periods of only a few days. So, and it does not fit together with the picture I just outlined about gas giants can only form far out in the system. So we have to at least modify our system about planet formation, our idea about planet formation. And over the last few years, people have came up with 2 groups of mechanisms, how these giant planets can move from the outside to the inside of the system. And one idea is that these planets interact with the disk, and they surrender angular momentum to the disk, and this way they spiral in. And the other group of ideas, which one could call high eccentricity migration, the planet achieves a high eccentricity, either due to planet-planet scattering or quasi migration, or quasi cycle, sorry. And whenever these planets have a very high eccentricity, the planet might come so close to the star that tides drain energy out of the orbit and the semi-major axis shrinks. And you end up with a gas giant on a circular orbit, close to its star. Now, of course, we would like to know which of these two does apply. So what would be a good type of observation to discriminate between these two types of theories? We could measure the inclination between the orbit of the planet and the stellar rotation. And this is either, you can either call this inclination or stellar obliquity. And the reason why this is a good way to discriminate between these two theories is if the planet would move in the disk, we expect it to stay in the disk. So we expect a low obliquity. If the planet has, for example, scattered, then we would expect that it's scattered out of the plane. So we would expect a high obliquity or high inclination. So how do we measure obliquities or inclination? Now it's pretty simple for our own star. We look at the sun, hopefully with something in front of our eyes, and we see some sunspots, and we see how the sunspots move over time. For other stars, it's not quite as simple because stars are point sources, even for the biggest telescopes. So we can't spatially resolve the stellar disk. What we can do, we can take a spectrum, and we would see a set of stellar absorption lines. And because stars do rotate, these absorption lines are broad. Part of the stellar surface is moving towards us, light is blue shifted, parts moving away, receding stellar surface, and we see redshifted light. So we learned something about the rotation of these stars. However, if we would now change obliquity like shown here, we rotate the stellar axis in the plane of the sky, and we then integrate again over the stellar surface, we would still see the same absorption lines. If we are lucky and this star has a companion who either, if it's a planet who transits or if it's a stellar companion who eclipses, then during these events, we miss part of the light. In this case, we miss approaching stellar surface area. So if we now integrate over the rest of the stellar surface area, our absorption line, which we will measure, will be deformed. And as the eclipse or transit goes on, this deformation will change. First blue shifted, then the red shifted light is missing. And one way to pick this up, to measure this, is we can determine the center of these absorption lines. And if we plot this as radial velocity, then we see this anomaly. At the beginning, we see a positive and later a negative shift. And if we now have a change in the angle between the stellar rotation axis and the orbital axis, this deformation change, as well as the radial velocity, which we would pick up. Now, this is not a particularly new idea. It's actually, people have dreamed of this already at the end of the 19th century, Mr. Holt, 1893, and it was measured a few years afterwards by Rosita McLaughlin, and these two persons also gave the name to this effect. And the first two measurements have been done in Beta Lyrae and Algol, and here on the x-axis, one can see the time. On the y-axis, the radial velocity in kilometers per second, and the orbital velocity is taken out here. So we can see first a positive bump and then a negative bump. These two eclipsing binaries are well aligned. And when we learned about the first transiting planet, HD 20945b, people already realized this would be a good measurement. And here you can see again, time focused on the mid-transit, and now radial velocity in meters per second, and one can see a positive and a negative radial velocity anomaly. This is an aligned system. The slope is due to the orbital velocity of the star. But we not only found aligned systems, we found misaligned systems. We found systems where the planet goes from one pole to the other pole, and we even found a couple of systems where the star rotates in one sense and the planet goes around in the other sense. So now we find planets of very different types of flavors. We found aligned systems, misaligned, and retrograde. Now this puts us in a tight spot because we took these measurements because we wanted to discriminate between these two types of series. So now it seems we are not able to do so. However, 2 years ago, we did found a pattern in the data, and that's what I show here. I now plot all the obliquity measurements available 2 years ago, the projected obliquity, as a function of the effective temperature of the host star. And I also color code cool stars, I make blue, red stars, host stars, I show the obliquity in red. And systems where the effective temperature is included, our boundary of 6,215 Kelvin is included in the 1 sigma error bar I show as a split symbol. And what one can see here is that all the cool stars tend to have low obliquities, good alignment between the orbit and the stellar rotation. While the hotter stars, there seems to be a more random distribution. So why could that be? Well, one way, of course, could be the planet formation is different between these type of stars. But that's kind of difficult to understand why that should be the case. Now, around this temperature of 6,250 Kelvin, something happens in the stellar structure. Cooler stars have a significant amount of the mass in the convective envelope, which I now show on the lower plot, while hotter stars basically only have a radiative envelope. This envelope is important in many different things, but one of the things where it's particularly important is tides. Tidal forces or tidal energy can be much better dissipated in a convective envelope than a radiative envelope. So that means everything else being equal, tides would have been stronger for the blue stars than for the red. That means we could also think we see this pattern because all of these planets had a high obliquity when they arrived near their host stars. But for the guys on the left side, we see low obliquities because they realign relatively fast due to tides. So one thing I should have said on the previous slide is I only plot here systems which are true hot Jupiters, meaning their orbit relatively close, orbital period less than 8 days, and the mass is at least 10% of the mass of Jupiter. In the next plot, I now show all the measurements which we have taken over the last 2 years, plus these, and also all systems. And as black dots, I show the systems where either the planet is less masses than 10% of Jupiter, which is actually hat P11, or the period is longer. So these guys are further out. And what we now see, of these black dots, that 3 seem to be exceptions to this trend which we have noticed before. And that's actually quite encouraging because if tides are important, then if you move the body which causes the tide further out, tides should be weakened. And also if our planet is less massive, tides should be less important too. So if tides are really causing this, then we might be able to sort these projected obliquity measurements as a function of tidal timescale, including now not only the effective temperature, but also the mass and the orbital distance. And that's what we have tried here. So let me walk you through this plot. Again, on the y-axis, we have the projected obliquity. On the x-axis, we have now a relative tidal dissipation timescale. And so that means that on the left side of the plot, we would see systems which would realign relatively fast, while on the right side of the plot, we would see systems where realignment would take very long. This tidal timescales we have calculated for the cool and hot stars with these 2 formulas I show on top, where Q stands for the mass ratio and A over R star is the scaled orbital distance. And these 2 formulas come from a paper by Zahn, 1977, and they've been calibrated on binaries, on synchronization on binaries, and not on alignment for planets. But that's the best we could find. So what we see is that nearly all guys on the left side seem to have a low obliquity, so that would be consistent. And the guys on the right side have high obliquities or more random, and now our exceptions from the last plot seem to fit in nicely, just because the orbital distance and the mass of the planet is taken into account. Now here's one exception. That guy there is hat P32, and it's shown with a split symbol because the effective temperature measured for this guy is really close to 6,250 Kelvin, it's 6,220. So if the measurement would have been a little bit larger, I would not have used the blue formula, but the red. And the guy would have ended up somewhere near Hercules 11. So this is clearly need of an expert, this calculation. However, what this plot does show is that all these guys, our measurements are completely consistent with that hot Jupiters had high obliquities when they arrived near the host star. So our measurements do tell us something. They do tell us that these planets had taken the high eccentricity road inward from the birthplace. Okay, so there was one important assumption we have put into all this reasoning, and that is that the disk, the gas disk and dust disk out of which a planet forms, is actually aligned with the rotation of the star. Again, this is motivated by what we see in our own solar system. There's only a 7-degree tilt between the plane of the equator and the ecliptic. But our colleagues tell us, or have told us recently, that this might be a naive assumption, and that, of course, star formation is chaotic. There are always magnetic fields. You have many stars are formed in binaries, which can actually lead to precession of the disk around the total angular momentum. And for more massive stars, internal gravity waves might also change the rotation of the outer layer. So what we could have happened is that the planet migrates in the disk was misaligned, this disappears, and we think what we measure here is planet migration, a sign of some scattering event, but what we see is a primordial misalignment with the disks. So how do we learn about the primordial alignment between stellar rotation and disk? Now, whatever is important for star-planet systems should also be important for star-star systems. Also, they form in a very similar way, same environment. So maybe we should check if these guys are aligned or misaligned. And I will now spend a few slides on measurements in closed binaries before then come back to the planet case. And this effect was known for over 100 years, this Rosetta-McLaughlin effect. So you might think you find lots of these measurements in the literature. However, I was hard-pressed to find only a few. And I guess that's because there's the understanding that closed binaries have aligned axes. And I will show later it's also quite difficult to measure these effects in equal mass binaries. But I did find one very nice measurement, again of Algol by Struve and Alvey from 1931. And time runs here in the y-axis from before, on top, and after eclipse. One can see how this magnesium-2 line is distorted when the planet, or when the secondary star moves in front of it. So because there have been so little number of measurements, we set out for little surveys. Binaries are not always neatly lined, survey or bananas. And we have 13 systems in our sample, and I show the eccentricity period here. And the measurement is, of course, easy in a binary system because the companion is much bigger. That's great. And I can show that here. This is measurement of Alpha Corona Borealis. It's a fast-rotating A star orbited by a G star. And time runs from the top left top to the right bottom. And we can see a bump in the absorption line, during the eclipse moves over the absorption line. This is again the magnesium-2 line. This is an aligned system. However, if we have a system with two stars that are about the same mass, then we have two sets of absorption lines. And during the eclipses, the radial velocity of these absorption lines is very similar. So now we can't take just the radial velocity of these guys. We would get a faulty result. So the way we do this is we try to model the set of absorption lines of both stars, including orbital movement plus eclipses. I'm now just going to introduce how we do this. So we have an absorption line, the star is rotating, it's on the left side out of eclipse, and then during eclipse, there are other broadeners, macroturbulence, and the point spectral function of the spectrograph. We have more than one line. This is the helium-1 line, the magnesium-2 line here. Helium-1 is pressure broadened. And we have two stars. So blue is now our secondary, red is our primary. And while the secondary is slightly less massive, you can see that during the eclipse, we receive much more light from the secondary foreground star. So we do have to take that into account. And of course, you need some data. And then you change your parameter. So here I denote the projected obliquity, or our observable we are main interested in, with beta. The planet people thought they would like alpha, lambda more, and lambda equal minus beta. So you will see now both symbols. Okay, so and the first system, or one of the first we measured this in, is dear Herculis. And you see on the right side pole-on view of the orbit. So we would look from inside the plane of the projection up here, and we see the system eclipsing. It's two very massive stars. The system is very young on a highly eccentric orbit. And what's interesting about the system is that the upside motion, which is measured in the system, is a factor of 4 too slow for what you would predict for the system given its system parameters. What is upside motion? Upside motion is a precession of the orbit in its own plane. And it's most easily, so after many rotations or periods, the orbit has rotated a little bit. And it's, for this type of system, most easily picked up by timing of the secondary and primary eclipses and how they change. And upside motion is caused by a GR term. It's also caused by the deformation of the stars. And they're mainly deformed by tides and by the stellar rotation, which kind of flattens the star. And if you would put a third body in the system, of course, this would change things too. So to illustrate the problem in the system is, I show now here the measured value of upside motion, arc seconds per cycle. Cycle is one period, including its uncertainty. This is a GR term, which is expected. So it's already in strong disagreement. If you include the effect of tides and the effect of stellar rotation, then there's quite some strong disagreement. And this was known for about 30 years. So people have thought about what could cause this disagreement. At the beginning of the 80s, people thought maybe GR is wrong. However, GR has passed numerous tests, so maybe it's good to look for a less costly explanation. Of course, there could always be another body in the system, but for this particular system, even a Jupiter-sized body could cause this disagreement. So this would be a theory which would be very difficult to falsify or to show that the planet is there. However, if the disks are misaligned, then this contribution to the upside motion due to the rotation, this flattening, would, after 45 degrees, would actually turn out to be a retrograde contribution. So it would, this could also explain this disagreement. So we went out and wanted to check if that's actually the case. We went to the OHB, observed the system during the two eclipses and out of transit, out of eclipse. And I show here two example measurements. On the top, again, the magnesium and the helium line, you see at this particular time, the radial velocity of the two stars was quite different. It's easily to pick up the two components. On the lower one, it's taken close to one of the eclipses, and you can't distinguish between the absorption lines from the two stars. This is one observation during the primary eclipse, and dashed blue is the model of our secondary foreground star. Red is the model of our eclipse primary. Black is the overall model, and gray is the data. And what you can see, this is a very poor fit to the data. This is our aligned model, best fitting aligned model. If you would leave the projected obliquity a free parameter, we receive a much better fit. And of course, we can do this with all the observations during the eclipse. So on left top, it's 4 hours before mid-eclipse, and on the right bottom, it's 4 hours after mid-eclipse. And this is again our aligned model, and it doesn't look too good, and we receive much better fit for the misaligned case. So we not only measure a strong misalignment of 70 degrees for the primary, we measure for the secondary a misalignment of 80 degrees. So, and coming back to the upside motion problem, that was the reason why we measured this particular system. If we drop the constraint that the rotation axes are aligned and put in our measurement, this histogram is what we receive. We receive this histogram with a tail because we haven't gotten any information about the inclination. So we have to integrate over all possible inclinations. So there's now a good agreement. And actually, after our result was published, people have reanalyzed some photometry and still in good agreement. So the problem here was that we have assumed aligned axes, but we shouldn't have. And one nice piece of physics as I find in this system is these stars are so close to each other, they're misaligned, so the stars should precess, just like tabletops. And the precession time scale is about 300 years. And these are eye measurements of the system. And so this is ours, and these are some from other from paper by Reisenberger and Geinen. And one can see that it does seem like the V-Sun eye measurements are consistent with this precession. Unfortunately, time scale is 300 years, so it will take a long time to see the full rotation. So we have taken data on 12 of our 13 systems, and we found some good alignment and some misalignment. And now coming back to the question about the planet system, we would, for example, expect, or at least I naively would expect, that we see strong misalignment for the guys who are out at long periods if the environment plays a strong role in misaligning the disk relative to the stellar rotation. But this is not exactly the picture we receive here. So it does not support the idea that there's a primordial misalignment. Of course, I argued before, yeah, we can look at star-star systems if we want to learn about star-planet system, but it's always better maybe to look directly at the star-planet system, and there would also be a way to do that. And that I would like to explain here. So if we have a system on the right side, a multiple planet system, and both of these systems have misaligned disks, the planets migrate inwards, the disks disappear, then we have in both cases strong misalignment, but for the case of the multiple system, the planet orbits are aligned with each other. So if you would measure good alignment between these two planets, but strong misalignment, then it would tell us that the strong misalignment for the hot Jupiters is actually due to primordial misalignment. If you would, however, measure overall good alignment in this multiple planet system, then we know that the primordial arrangement was good alignment, and that the strong misalignment we now see is actually due to some scattering event or the planet migration. So that leaves us with finding these planets, these multiple transiting planet systems, and the best way to do this is Kepler. Kepler was launched a couple of years ago. It looks at the constellation Cygnus. It monitors 150,000 stars continuously for a couple of years and always sees, and this way it finds planets. I found already over 2,000 planet candidates. Because the data is so nice, most of these planets will turn out to be real planets. The main goal of this mission is to measure the abundance rate of Earth-like planets in the solar neighborhood, or eta Earth. But of course, it's very good at picking up multiple transiting planets. There's one drawback to this, because Kepler host stars are on average relatively faint, and transiting multiple systems on average being less common or being more difficult to pick up, these guys are even more faint. So this is Kepler 25, one of these multiple systems. We measured the Rosetta-McLaughlin effect here with the 10-meter Keck telescope, and yeah, you see the radial velocity, and what you don't see is such a nice effect like you have shown you before. It's very difficult to find here. And it's also the case because these planets, the multiple systems, tend to be relatively small. Nevertheless, we can look at this data carefully, and we can analyze it, and we do find that the data tells us that we have a good alignment here. I can explain you later if you want why our algorithm finds this type constraint. However, I would argue that this is not very satisfying because it's very difficult to find the Rosetta-McLaughlin effect by eye. So we thought about, is an alternative way how we can measure the obliquity in this system, and we think there is. So we have this beautiful spectra delivered by modern spectrographs. But often we only use part of it. We want to measure the radial velocity, and then we measure the iodine, only measure the radial velocity in the iodine region. Other region, for example, the blue region here, is not used. But even more importantly, however we measure it, we always only measure a radial velocity. We have the spectra, and we measure we have one measurement. But these spectrographs allow for more. We can actually measure the absorption line shape of these spectra. So what we thought is we could take our algorithm I've introduced before from the binaries, where we look at the absorption line shape, and use it also in these systems. And the good thing is, okay, the signal is smaller, but the good thing is these are all late-type stars. So we have hundreds or thousands of lines. So we can add them all up, and we receive a very high signal-to-noise line. And then we can just look for the missing light component if the planet moves over the stellar surface area. And because first time we used it for planet systems, first we didn't look at Kepler-25, but at HAPI-2, which is a relatively bright, hot Jupiter. And on the y-axis, I've now the time from before to after transit. The dashed line shows first and fourth contact, so begin and end of the transit. And on the x-axis is the rotation speed of the star. What we see is we see this nice dark bar where we have missing light, and that indicates that the system is well aligned, and also that our algorithm works. Now we can go to Kepler-25, the multiple transiting system. And of course, the signal is somewhat fainter, but one can still see it. There's a component of missing light from blue shifted to red shifted light. And if we subtract our best fitting transit model in the middle panel, then it seems to be only noise left. And again, also this, analyzing this different part of the spectra, we again find good alignment. So what we have done here, we have taken two different parts of the spectra, the iodine region and the blue region. So we took 100 nanometers blue width of the iodine here. And in both cases, we find good alignment. And we also analyze these two data sets. It's the same data set, but different spectral region with a completely different algorithm. And what I show on the right is now I bind the radial velocity, and I overplot a model, a radial velocity model derived from our best fit to the planet shadow. So over the last few months, actually, there have been a few other measurements of not only Kepler-25 was measured in the obliquity, but the first one was last summer, Kepler-30 by Roberto Sanchez, and he looked at a later type star where you have lots of star spots. And by looking at the planet moving over the star spots, you can also derive very nicely the obliquity. There have been Hirano measured the obliquity in KOI 94. KOI stands for Kepler Object of Interest, but this is also a planetary system. And then there have been two other measurements, not of the projected obliquity, but of the inclination using astroseismology and the splitting of modes. And all of these 5 measurements receive good alignment. And also, the system, because either the planets are far out or they're very small, it's unlikely that these have been influenced by tides. And now what we can do is we can make a little Monte Carlo calculation. How often, if we take from a isotropic obliquity distribution, how often would we receive these type of measurements? And that's not very often. It's very unlikely that these obliquity measurements in multiple planet systems are actually coming from a similar distribution, isotropic distribution, as the hot Jupiter measurements. That means multiple systems have always good alignment, and the hot Jupiters have their high obliquities. That's due to high eccentricity migration. So I've talked already a little bit about that I like to look at the absorption line shapes, and I think this is not only useful in Rosetta-McLaughlin measurements, the one I've shown before, but also looking at the shape might be useful in radial velocity measurements. And that is because we have this new set of spectrographs that delivers better data than we are used to. So we should look how we can exploit this data better. And a few months ago, there was this, I guess you all know about this nice result by Xavier. And he and co-workers have found a planet around Alpha Centauri b. And this planet actually has a mass, pretty much the mass of our own Earth. It's just very close in. And what's amazing about this measurement is that can measure a radial velocity amplitude of only ½ meter per second. And it was quite difficult because alpha cent B is a relative, it's a relative active star. So these are the data sets, 2011 on the bottom, then 10, 9, and 8. And you see that the amplitude or the scatter here is higher than 0.5 meter per second. And that's not due to the orbit, to the pole of the planet, but due to the fact that the star is active, there are presumably star spots on the surface. And if you have a star spot, less light emitted from the region because it's cooler. The star spot with the stellar rotation rotates around. So you receive first blue shifted, then redshifted light, you receive an RV signal. And they knew about the rotation period of the star. So what they have done for each of these seasons, they have fitted sinusoids of the period or a double of the period of the stellar rotation to it to subtract these signals. Or they have also done some other interesting things or good things, but this was the most challenging part, I think. And after this, they received, so this is now the radial velocity data. There are 460 points shown in orbital phase of the planet, and the red dots with the error bars are averaged data points. One can see the orbital signal. Now, they have to reduce, or they had to reduce identify and remove the signal due to star spots in the radial velocity. But I think it might be also an interesting way to try to do this before you measure your radial velocity. You look at the absorption lines itself. And that is because star spots change the shape of the absorption line. And when they move over the surface, there's a change in the shape, in this deformation. So it's while the planet actually does shift the whole spectrum. So first, trying to identify this particular noise, removing it, and then measure radial velocity might be better. And this is a little similarization I've done. And you see on panel A, a star with 3 active regions. You see in C, the absorption line, in D, the deformation on this particular absorption line due to these 3 active regions. And then next to the active regions, I've put also a planet in the system on orbit of 110 days. 3 times the mass of Earth, so it's a very small radial velocity signal. And in panel B, you now see the radial velocity we would measure, mainly due to the star spots. And then I fitted off the simulated absorption lines. I try to fit the shape, subtract the deformation, and then again measure the radial velocity, and that's what we see in panel E. Of course, this is only a similarization, but I think that looks quite promising. And I guess because I'm coming here from MIT, I also feel like making a little bit commercial at the end. So this is what we see here is planets found, transiting planets found by Kepler in blue and other planets. And this is the size of the planets on the x-axis and the y-axis, the brightness. And what we can see, so there has been this over 2,000 planets found, but most of them are around faint stars. So what we really would like to populate in this diagram is the upper part. And one way to do that, hopefully in the future, is a test satellite, transiting exoplanet survey satellite, where George Rieker from MIT is a PI, and they just had a site visit, and there's also one other competing mission. So one of these 2 is getting selected. But if this one is getting selected, then this one will monitor the whole sky, a patch of sky for 1 month, and then it will do this for 2 years, so cover the whole month. And it will this way detect, hopefully, planets like this. So follow-up will be much easier. Okay, that's it.
Yeah, thank you very much. Now we have some time for questions. So please go ahead.
Of course, this kind of simulation that you did to show what the effects would be, one could subtract the effect of the spots. In reality, it would be tremendously more complicated than that because of the, in addition to the spots, you will have, plage and other bright areas. The lines, would be intrinsically symmetric from the start because of convection, etc. In reality, I think if you fold in all of those other effects, it would be much, much harder than this simulation suggests, right?
I agree. The simulation practice turns out you always forgot something. However, I did include here the PSF of the spectrograph, convective blue shift, and microturbulence, and some natural broadening. But what I assumed here is I assumed a shift. So I assumed that the PSF stays absolutely stable over the whole observations. Even you can argue if that's the case or not. I assumed a relatively low error in the wavelengths of the calibration of the spectrograph. I think I used 20 centimeters per second. That is the design goal of HARPS North. It's not reached yet. So there are a couple of, you could argue, optimistic simulations in here. But the point, I guess, why I put this up is that often we only look at radial velocity because we are used to spectra, from instruments which are a little bit older. But now with a couple of spectrographs, we have access to much better data, and I don't think we use it to the full extent.
More questions?
Thanks for the talk. It was very clear. It's very difficult to present all these complicated results with binaries and with orbitals. It's also clear. So thanks for that. One comment, one question. Can you please clarify the physical reasons why the tidal forces changes at this particular temperature of the star that you mentioned, 6,200 something? Okay.
Let me just go back. So maybe this is the best plot to show this. So the 6,250 Kelvin, it's somewhat arbitrary. I show you another plot later. But about the reason why we picked this temperature, or we could have also picked 6,100 or 6,400 Kelvin, is because the mass in the convective envelope here in solar masses, as a function of effective temperature, this is for zero-H stars, zero-H main sequence stars. It really kind of drops here. So what we have observed in binaries is that the time it takes to circularize orbits due to tides, or also to synchronize the rotation so that the orbits face each other at the side, like the moon does to the Earth, it takes much longer for these type of stars than for this. And this is thought because in this convective envelope, the tidal energy from this bulges, this tidal bulges, is dissipated much faster. I don't think we have a very good, clear understanding how this dissipation works in either case, for the radiative envelopes or the convective one. The shortcoming of our particular choice of having these two tidal time scales is you can see for Herculis 32 up there. So this is not ideal, but so far there's, at least I wasn't aware of, another very good theory round which you could use. So let me show you one other, but I think which might be interesting. Another way you can see that something is happening around this temperature is that stars, when they're born, rotate relatively fast, while we observe for late-type stars a relatively low rotation speed. So these are our stars from the obliquity measurements and Spock's stars, the small ones here. And the further you go to higher temperatures, the faster they still rotate. And part of this is thought is due to the fact that for these guys, because they have a convective envelope, they have stronger magnetic field which couples them to the wind, which then ionized stellar wind, which then slows down these stars. So this is just a particular temperature where there's lots changing in the stellar structure.
Thanks also for a clear and nice talk. Question on the the results from the banana survey that you showed. So I saw there's only one case of a measurement of a misaligned binary, right? If I remember properly.
Yeah.
So the question is...
There's three.
There's three?
Yeah, I showed only one.
Okay, you showed one. There's three. The question is if you know or if you can already estimate what's the fraction of binaries that are not neatly aligned. And if that fraction is small, you could change that not always to nearly always, right?
Yeah, so I guess what's a fraction? It's a question I am not able to answer because our sample is not unbiased. When we selected our stars, we picked particular type of stars. First of all, we wanted to cover certain orbital distance, but then we picked some stars where we knew there's a third body, just because a third body could change things. Some stars which we have noticed that there's something strange going on, like Dia Herculis. So we can't extrapolate from the fraction of misalignment we found in our sample the overall one, and also they have different ages. But what might cause this? Of course, the third body is a prime suspect for via Kozai cycles. However, in two of these systems, of the three systems, for example, Dia Herculis, there's no third body known, also not in Civi Velorum, only in our third system, which is misaligned. We know there are a couple of other bodies in the system. So far, we don't know what's the exact reason for the misalignment and how many stars are influenced.
I have a very naive question coming from someone that doesn't know the field good enough. But why are the planets always moving in and not out? Why do they migrate inwards?
Yeah.
And you don't contemplate a scenario where they migrate outwards?
Yeah. So this migration, which I touched on very briefly at the beginning, depending on the parameters I'm not an expert on this, but depending on the parameters you put in, you can also have outward migration. But it seems like all the people I talk to, they think, if at all, most of the time, inward migration is happening. And it's not that this migration, that our data suggests that it's not happening. For example, in our own system, we know that Jupiter and Saturn have migrated via this migration. The question is this migration responsible for moving the gas giant from a couple of AU inwards to a small fraction of AU, or if there's also something else happening? And that's what I try to address here. And yeah, there's two types of this migration, 1 and 2. One is this opening of gap, and one without.
I also have a question. And why is Kepler actually detecting only planets from the lower brightness stars?
Yeah,
like you showed it in the plot. And what is the advantage then, other than a better follow-up to detect brighter stars?
Yeah. So Kepler looks at I think 10 by 10 square degree plot on the sky. So you only have so many bright stars in there. But Kepler was really designed with a question in mind. We want to know about how often do we have Earth-like planets? So Earth's mass at 1 AU around a solar type star. So for this, you want to send as many you want to measure for a couple of years to see a couple of times an Earth-like planet transiting, and you need lots of stars. TESS or similar missions like Plato have in mind to cover a much. They can't hunt for Earth-like planet because TESS will only observe for months a given part of the sky. The advantage of it would be we would find the brightest one, and we could study these in more detail via transmission spectroscopy during the transits. So it's a trade-off for what you want to learn about.
Okay, thank you very much. If there are no more questions, then we can slowly walk over to the library and have a bit of coffee. And yeah, let's thank Simon once more for this great talk.